Hello everyone, welcome to the fifth lecture of the lecture series Signals and Systems. In this video, we'll see some examples and insights into the convolution operation, and we'll see systems represented by differential equation. So let's get started. So first we have the convolution operation. So the operation and integral are synonymous because in continuous time it is actually an integral. So in the previous lecture, we saw how it is represented. So convolution between two signals, x1 of t and x2 of t, is given by integral minus infinity to infinity, x1 of tau, x2 of t minus tau, d tau, right? And we saw, especially for the LTI systems, the output y of t and input x of t is related by the impulse response h of t as follows. So y of t is nothing but x of t convolved with h of t, which is nothing but integral x of tau h of t minus tau d tau. So I'll just summarize whatever we discussed in the last class, right, on how to find this integral graphically. So summary of the graphical procedure. So first, what did we do? We took x of tau as it is, right? So x of tau is taken as it is. And next, we need to deal with h of t minus tau. So how did we obtain h of t minus tau? So first, take h of tau and perform a time reversal. So again here, to find h of t minus tau, you can first do the reversal and then take the time shifting, or you can do the time shift and then do the reversal. But it will vary accordingly, right? We already saw how those two procedures vary. So now, for simplicity, let's say we first do the time reversal. Okay. Perform time reversal to obtain h of minus tau. And then to obtain h of t minus tau from h of minus tau, what should we do? So we should actually right shift h of minus tau by t. So right shift h of minus tau by t units along the tau axis. So what will happen? That is h of minus of tau minus t, right? This is the right shift. So this will fetch you h of t minus tau. So once h of t minus tau and h of tau is there, now to find y of t, multiply x of tau and h of t minus tau and integrate. So this may be at some particular t naught, right? So this, let's say t naught and t naught here. So this will give you y of t naught. So similarly, I have to repeat the same procedure for all t. Repeat the procedure for all t. Okay. In general, we can actually divide them into regions and then integrate. So in general, divide the time axis into certain regions and find y of t in that particular region one by one. So 1 by 1. Okay. So this is the summary of the graphical procedure. So we already saw one example in the last class. So example 1, we actually took x of t to be e power minus at u of t and a greater than 0, and h of to be the unit step function itself. And we obtain y of t to be 1 by a into 1 minus e power minus at u of t, right? And we also saw several other properties, like if h of t is delta of t, then and x of t, let's say it's remain same, then y of t will be x of t convolved with delta of t, which is nothing but x of t itself. So let me call it properties. And if h of t is some delta of t minus t naught, then y of t is x of t convolved with delta of t minus t naught, which is nothing but x of t minus t naught. So if it is plus t naught here, you will get x of t plus t naught. So next let us consider for h of t equal to u of t. So we know y of t is x of t convolved with u of t, and which is nothing but integral x of tau u of t minus tau d tau. But we know that u of t minus tau is equal to 0 for t minus tau less than 0, right? So this implies that for tau greater than t, u of t is 0. So this term is going to be 0. So the integral will only go from minus infinity to t. So y of t is integral minus infinity to t. And in that region, this u of t minus tau is 1. So it will just be x of tau into d tau. So this you can see is just the integration. So convolving with the unit step function gives us an integration. So you can actually see some pattern. When you convolve with the unit impulse, you actually get the same function, same signal. And unit step function is nothing but the integration of the unit impulse. And when you convolve it with the unit step, you actually get the integration of the input signal itself. So the next property is a follow through of this. So we convolve two unit step functions. So this is nothing but integration of the unit step function, which is nothing but the ramp function. Ramp function. Right? So again, if you convolve this ramp function with u of t, you will get a parabola kind of dependence. So this is like x, and then if you again integrate, you will get x square. If you integrate that, you will get x cube, and so on. Okay. So let us see another example. A simple example. Example 2. So we take x of t to be, let's say this is the signal. It extends from minus t1 to t1, and this is 1. Okay, this, let's say, time axis, and this is x of t. And let's take h of t to be same, but here it is, let's say it's from t2 to minus t2 to plus t2, and the amplitude is 1. And let's say t2 is less than t1. Okay. So now we want to find y of t is equal to x of t convolved with h of t. So what we have to do? So we first take x of t as it is. So we write it as x of tau. So this is in the tau axis. This is x of tau. And then h of t, what we have to do? We should actually invert it. So if you invert, since it is symmetric, you will get the same. h of minus tau, and then you have to right shift by t naught, correct? So h of t naught minus tau. So this will be tau. If you right shift, this will move to t naught minus t2 and this will move to t naught plus t2. Okay, so now we need to multiply these both. Consider these both signals. And then multiply them and take the integration. So we can have many regions, right? So to just, to just show that t2 is less than t1, I'll put a shorter pulse. Okay. So now this t0 can be in any region, correct? So in the first case, let us take this is actually somewhere over here. So this was the axis. This was t0 plus t2. This was t0 minus t2. So this t0 plus t2 is actually less than minus t1, which means t0 is less than minus of t1 plus t2. So in this case, there is no overlap. Overlap between x of t and h of t. So y of t will actually be 0 for t less than minus of t1 plus t2. So in the next condition, let us see. So this is going to be same. Okay. And h of t naught minus tau. So what we say is that so t naught plus t2 and t naught minus t2. So this minus t1 is actually between t naught plus t2 and t naught minus t2. Okay. So in that case, you can see there is some overlap. And what is the region of overlap? Region of overlap is minus t1 to t naught plus t2. And x of t into h of t in that region is actually 1, right? H of t minus tau. X of tau into h of t minus tau is equal to 1. So y of t in this particular region will be integral. So minus t1 to t naught plus t2. So this we took as t naught, right? And this is actually 1 into dt, d tau, which is nothing but t naught plus t2 minus of minus t1, which is equal to t naught plus t2 plus t1. If you want to write in terms of t, y of t is nothing but t plus t2 plus t1. So it is actually ramping up with time. And what are the limits for t? We can find it from here. So in the first case, t minus t2 less than minus t1 implies that t is less than t2 minus t1. And in the second, minus t1 less than t plus t2 implies that t is greater than minus of t1 plus t2. So for t less than t1 minus of t1 plus t2, we got y of t as 0. And then for it little greater than t1 plus t2 minus of t1 plus t2 and t less than t2 minus t1. Since t2 is actually lesser, we can write it as minus of t1 plus t2, t1 minus t2. Okay, so in this region, y of t is actually t plus t2 plus t1 for minus t1 plus t2 less than t less than minus of t1 minus t2. Okay. So now in the next case, what will happen to h of t? So let me draw a line here. So in next case, let's say all of this is inside, all of h of tau is inside x of tau. Okay. So then I have x of tau like this. and h of tau somewhere like here. So this is t naught minus t2, t naught plus t2. And what are the limits for this? T naught minus t2 is actually greater than minus t1, and t naught plus t2 is actually less than t1. So this gives t naught greater than minus of t1 minus t2, and this gives t naught less than t1 minus t2. Okay. So now what will be the integration? It is like the entire region, right? So y of t naught is integral. This product is anyway going to be 1 between x of tau and h of t naught minus tau. So 1 d tau. Limits are, since this entire h of tau is inside x of tau, only the limits will be from here to here. So it is t naught minus t2 to t naught plus t2, which is nothing but t naught plus t2 minus of t naught minus t2, which will give me 2 t naught, or t naught gets cancelled, which will just give me 2t2. Okay. And so y of t is equal to 2t2 for t greater than minus t1 minus t2 less than t1 minus t2. You can see it is like a continuous regions. If you see, this is less than minus of t1 plus t2, and then this answer was between minus of t1 plus t2 to minus of t1 minus t2, and here we have minus of t1 minus t2 to t1 minus t2. So next, again we will have x of tau as same. And h of t naught minus tau we actually have somewhere here, where t1 is actually between these 2 points, t naught minus t2 and t naught plus t2. So t1 is greater than t naught minus t2. This implies t naught is less than t1 plus t2, and we have t1 less than t naught plus t2. This implies t naught is greater than t1 minus t2. So in this region, what is the overlap? Overlap region is t naught minus t2 to t1. So y of t will be integral t naught minus t2 to t1 1 into d tau, which is nothing but t1 minus t naught plus t2. So this is t1 plus t2 minus t naught. So this is a lowering ramp, right? This way, it decreases with time. This is y of t naught. So y of t will be t1 plus t2 minus t, and the limits are for t1 minus t2 less than t less than t1 plus t2. We can actually replace t naught with t, like even in these definitions, right? It will just simplify our convention. Okay. And the final step is when h of t naught minus tau is actually outside this region. So finally, when t naught minus t2 is greater than t1, which implies t naught is greater than t1 plus t2, then there is no overlap and y of t equal to 0 in this region. So y of t equal to 0 for t greater than t1 plus t2. So now let's just consolidate all the definitions. So first, what did we have here? So y of t equal to 0 for t less than minus t1 plus t2. Okay. 0 for t less than minus of t1 plus t2. Okay, and then what did we have? T plus T1 plus T2 for between this two. Okay, T plus T1 plus T2 minus T1 plus T2 less than T less than minus of T1 minus T2. And then what did we have here? 2T0 for this region. 2T2 for minus of T1 minus T2 less than T less than T1 minus T2. Correct? Right. And then T1 plus T2 minus T. So minus T plus T1 plus T2. Right? For the limits T1 minus T2 to T1 plus T2. And finally it is actually 0 for T greater than T1 plus T2. So you can see all these are continuous regions. So I of T is this. Now we can try to plot it graphically. So I of T. What are the regions we have? We have T1 plus T2, right? And then we have minus of T1 plus T2 and T1 plus T2. And then we have T1 minus T2, minus of T1 minus T2 and T1 minus T2. Right? So now we are ready to plot. So in this region, the signal is y of t is 0. And then it ramps up to. So what will be the final value here? It starts from actually 0 and goes up to minus of T1 minus T2 plus T1 plus T2. So it goes up to 2T2. Right? So 2T2. This is 2T2. And it stays in 2T2 from here to here. And then again it ramps down to here. It starts from 2T2 and goes to 0. Right? So it goes to 0. So this is y of t. So I will also draw x of t and h of t so that we can infer something from this. So this was x of t from minus t1 to t1. And then this was h of t from minus t2 to t2. So if you see y of t, convolution. So y of t extends from minus of t1 plus t2 to t1 plus t2. So if we have the width of the signals, right? Width of x of t is equal to 2t0, t1, right? Minus t1 to t1. The time interval where x of t is non-zero. And we have width of h of t is 2t2. And what is the width of x of t convolved with h of t? This is actually 2 into t1 plus t2. So it is the sum of these two widths. So in general, x of t can be any signal. So in general, say let's say this is x of t. This width is, let's say, some t1 convolved with some h of t. Let's say this width is some t2. Then the resulting signals y of t width will be t1 plus t2. This you can also obtain mathematically from the convolution definition. Minus infinity to infinity x of tau h of t minus tau d tau. You can see when we define this such that like this, the overlapping function will just be when t1 and t2 are actually present. So for example, if I rotate h of t and then push it by T naught minus tau, right? So I will actually have it something like this. And this starting point will be actually pushed T naught, right, from here. So from wherever it was there, let's take this as the initial signal. It is being pushed by T naught. Actually, it is the right shift, right? So let's do like this. So let's say this was the initial signal, and then it is being pushed by T naught. So this is T naught. So initially, if it was at some A, this will be at T naught plus A. And if this was at B, this will be at T naught plus B. So the overlap is possible only when, let's say, this places are C and D. Let's say this is A and B. When you actually flip it, right, this will become B and A. So you have A and B after flipping. So you have like this. Okay, let me take this as A and B itself. So this will actually be B and A because you're flipping and then right shifted, right? So what will be the overlap? So D equal to T naught plus B. This is the time after for T naught plus B greater than D, right? T naught plus B greater than D, there is no overlap. And what is the other case? T naught plus A less than C. Again, there is no overlap. So what are the time variables? So T naught is greater than D minus B and T naught is less than C minus A. So actually for T greater than D minus B and less than C minus A, only in this region y of t is non-zero. Okay. So what is the width of y of t? Width of y of t is nothing but C minus A minus of t minus b, which is nothing but C minus A minus d plus b. So you can just take these two terms together, minus plus b minus A. And if you see C minus d is nothing but this extent, right? So it is actually, again I think there is a factor of minus missing because when you flip it, this will actually go to minus b and minus a. So this is minus b and minus a. So here it will be minus b minus a. So it is d plus b and t naught less than c plus a. And this should actually be the opposite, right? Where there is overlap. Where there is overlap, it is actually t naught less than d plus b and t naught greater than c plus a. So this will be t less than d plus b and t greater than c plus a. So this will be d plus b minus of c plus a. So now you can see d minus c plus b minus a. So, and this is nothing but width of x, correct? D minus c plus width of y. Okay, so I'll explain it once again because it's little confusing. So let us take x of t is having extent only from c to d and which is of length t1 or width t1, and h of t is having extent of a to b of width t2, and we want to determine what is the width of y of t. So from the definition of the convolution integral, we have this, and from here using the graphical representation we can actually see when we do h of t minus tau, the signals will vary from t naught minus b to t naught minus a, and we can find the regions where there are no overlap. So if t naught minus b is greater than d, then there will be no overlap between h of t and h of t naught minus tau. So that is one condition. And on other condition, t naught minus a is less than c, then also there is no overlap. So when there is actually overlap only, you will have y of t. So that will only determine the width. So when there is an overlap, when t naught minus b is less than d, which gives t naught less than d plus b, and also when t naught is greater than c plus a. So actually t is varying between c plus a to d plus b. So y of t is only non-zero inside this condition. Then we can easily find the width. Width is nothing but the upper time minus the lower time. And when we just rearrange the terms, we see that it is nothing but the width of x plus width of h. So this is h. So this is always true for any signals x of t, h of t, right? So this is a very good interpretation and will be helpful in many cases. And also for this particular example, we saw this, right? So we'll also see what happens when t1 equal to t2. So t1 equal to t2. So both h of t and x of t we have minus t1 to t1. So this will go to minus 2 t1, right? And this will go to 0. And this also goes to 0. And this is going to 2 t1. So this will actually look like this. I'll draw separately. So it starts from minus 2 t1, increases up to 2 t1, and then again decreases at 2 t1 and goes to 0. So this is y of t. Okay. So you can actually see the slope of these are 1 and slope of this is minus 1. Here also it was the same case, right? Here also the slope is equal to 1. Here's the slope was minus 1. Okay. So next we will see a special class of systems called as described by linear constant coefficient differential equations. Linear constant coefficient differential equations. So a good example is like dy by dt plus y of t equal to some dx by dt, let's say dx by dt plus 4x of t. So what linear means is each of these terms, the degree, right? So degree is the power of the highest order, and order is the maximum, like how many differential equations are there. Like d by dt is, if this is the maximum in the differential equation, order is 1. If it is d square by dt square, then order is 2. And whatever the power this highest order is raised to is called as linear. The degree. The highest, the power of the highest degree. Highest order is called as degree. For example, I can have terms like d of t, dy of t by dt whole square, right? So this is like degree 2. Power is 2. And if it is the highest order, then the degree is also 2. So we are dealing with linear. Linear means the degree is 1. And in general, the power is also 1. And constant coefficient, what it means? So you have coefficients of like dy of t is 1, y of t is 1, here 1, and here it is 4. So the coefficients of the derivative terms. And y of t is also considered as like derivative term with order 0, let's say, right? Terms is constant. Okay. And actually this is one class of linear time invariant systems. That is the system, the LTI system's input-output relation is described by this differential equation. And you can see it is an implicit definition, right? Implicit relation. What it means is like y of t is also part of the equation. So y of t, the output is also part of the equation. Explicit is, so output alone comes on left hand side and x of t is describing the entire right hand side. So y of t is explicitly stated in terms of x of t. This example is y of t is equal to x of t plus 1 and so on. Okay. So if it is implicitly stated as in the form of this differential equation, we actually need to find the solution to find the explicit form. So we need to find the solution of the differential equations. To find the explicit relation. Okay, so we'll just go ahead and see an example. So we'll consider the differential equation dy of t by dt plus 2y of t is equal to x of t. So in general, the differential equation will have two solutions. So one is the homogeneous solution. So this is nothing but when input is 0. So dy of t by dt plus 2y of t equal to 0. So this will give the homogeneous solution. And let's say it's represented by hy of t. And this is also called as the natural response of the system. And the other one is particular solution. So this is for the case dy of t by dt plus 2y of t equal to x of t. And this is normally called as the forced response, because the input is actually forcing this output. However, here it is just the natural response of the system itself, because without any input, it is still giving some output, right? So you may ask how for a linear system without any input there can be some output, right? So that will depend on the initial conditions. So the natural response depends on initial conditions. So describing these initial conditions, actually it's like giving some inputs. And the output is actually as you can see, the addition of these both outputs. The output is, we can say, superposition of the natural and forced response. So the system is still linear. Okay. So now let us try to solve this. So let us first find the homogeneous solution. So dy of t by dt plus 2y of t equal to 0. So initially we actually every differential equation we assume that y of t is something like a e power st, and then we try to find s and a. So s will be directly found from the differential equation, and to find a we need some initial conditions. Okay, so if we put this equation here, differentiation of e power st will be s e power st. So it will be as e power st plus 2 e power st equal to 0. So a e power st is common. We get s plus 2 equal to 0. So it is just nothing but s is equal to minus 2. So our y h of t is nothing but a e power minus 2t. So now let us find the particular solution. So for this we look at the input. I think here the input is something like x of t is equal to k e power 3t u of t. Okay. So what will we have on the right hand side? So dy of t by dt plus 2y of t is equal to k e power 3t u of t. So now we need to take this y of t in some form of the input itself. So we assume y of t is equal to some y e power 3t. And the u of t is there. So it means that the input is only coming after time t equal to 0. So for this case, we can still assume that it is still valid. So we'll get 3y e power 3t plus 2y e power 3t is equal to k e power 3t. So we get 5y is equal to k and y is equal to k by 5. So what is the particular solution? This we are considering for t greater than 0. So it will be k by 5 e power 3t for t greater than 0. For t less than 0, it is actually the same as the homogeneous solution because the input is 0. So what we have the final equation as? So y of t is equal to a e power minus 2t plus k by 5 e power t 3t for t greater than 0. So to find what it is at all instance, we need to have an initial condition. So let us take this condition. Since x of t is equal to 0 for t less than 0, let us also assume y of t is equal to 0 for t less than 0. This is nothing but the condition for causality. Right? So we say at y of 0 also it will be equal to 0. So if you apply that condition, we will get a plus k by 5 is equal to 0. Or in other words, a is equal to minus k by 5. So now we get the entire response. Y of t is equal to, what did we get? K by 5 into e power 3t minus e power minus 2t into u of t. Because the output is going to be 0 for t less than 0. Right? So we were able to find a from this initial condition. And also we saw that y of t is can be defined for all instants of time using this causality condition. So these kind of equations are common when you try to solve an RC network or RLC circuits. So what we actually get is these kind of differential equation and we need to solve them. So if you have some system with RC elements and you have x of t as input and y of t as output. In general, we'll have a relation like this. Summation k equal to 0 to n ak dk y of t by dt power k is equal to summation. Here we can take some other. M equal to 0 to m bk d bm dm x of t by dt power n. And let's this side take as n. Okay. We'll have some relation between input and output as follows. And we may need to solve them to find it. And we add the condition y of t equal to 0 for t less than 0, or in some situation t less than t naught, and x of t equal to if x of t is equal to 0 for t less than 0. This causality condition. This is called as the zero state condition. Because when before the input arrives, the output is actually in the zero state. So in the coming lectures, we'll also develop some tools to analyze these types of LTI systems in more detail and more easily. And there are many powerful methods and also very good special characteristics and properties of these LTI system, which we'll see later. So that's it for today. Go back, revise, learn your basics thoroughly, practice a lot. Take care. Bye.